Alrighty, boys and girls, ladies and gentlemen, welcome back to another scintillating episode of Mr. Smith Talks About Calculus. Happy New Year. And we're going to continue with what we started in the last lecture, our journey through section 4.1 on anti-differentiation. And so without further ado, let's jump on in. If you have not watched the first part of these notes, you should go back and do so. The big idea that we set up in that was that this process of finding an antiderivative is the inverse process to finding the derivative. And kind of big picture, that the derivative is giving us the ability to break down quantities into their instantaneous changes, kind of pulling them apart. And the antiderivative, or as we'll come to call it, the integral, is going to be able to put that back together. So kind of two different directions in that process. And with that, what we saw in our first section was that a function has one derivative. Okay, you have a function, you differentiate, you come up with one outcome. A function can have multiple antiderivatives. And we saw that with our first illustration, that because both big F and big G yielded the same derivative, they both act as antiderivatives to that function. And that's sort of where we left off yesterday, was that two different functions can have the same derivative, or the other way, one function can have different antiderivatives, but just by a constant. And then we kind of marched through a few different formal definitions of that idea, that if a function's antiderivative is the function that then yields that as the derivative. So you get a little bit tricky going back and forth like that. But I think the easiest thing is you start with a function, the antiderivative of that function is the thing that when you differentiate, gets you back to where you started. And that's what we're going to be doing today, is starting to actually find some antiderivatives and seeing how it links back to our theorems on differentiation that we spent the first semester looking at. So without further ado, we'll start there, that this idea that because this process that we're now calling anti-differentiation, this process of finding an antiderivative, is the inverse of differentiation. The theorems for anti-differentiation are just derived from those, or obtained from those that we have on differentiation. It's kind of like a one-to-one matchup. The anti-differentiation theorems are obtained from those on differentiation. And we're going to just blitz through a bunch of theorems and then do some examples. Just like with differentiation, polynomials are going to be kind of our bread and butter easy cases. And you're basically just going to be using those same ideas from the derivative of the power rule and breaking apart bigger expressions into smaller ones. So we'll kind of run through those, and I think you'll start to see those pretty quick. As we progress, we'll start to do some non-polynomial functions. So throw in some rational functions, some radical functions, and see that we can kind of fake our way through those by trying to make them into polynomials. Because we're not going to immediately have a way to work through rational functions like we did with differentiation. Okay, so here we go. The first and most basic theorem is kind of the analog to the identity theorem for derivatives. That the antiderivative of 1, so the antiderivative of dx, there's really an invisible 1 here. The thing that's going to yield that is x. Okay, derivative of x is 1, and so the antiderivative of 1 is x. However, because of that idea that there are multiple antiderivatives for any given function, we're always going to add in this plus c, where again, c is just some constant. You've got x plus 7, the derivative is 1. You have x minus 7, the derivative is 1. Okay, so x plus c is the antiderivative of 1. And then kind of tagging on to this one is that if you have a constant in front of a function, you can pull out that constant, that the antiderivative of a constant times a function is just that constant times the antiderivative. So in notation, we've got this antidifferentiation symbol. The antiderivative of a times f of x dx, where a is just some constant, is just going to be that constant times the antiderivative of that function. Just like with the derivative, we're also going to be able to break apart polynomials so that the antiderivative of sum is the sum of those antiderivatives. And even going further back, these all kind of come back to some limit theorems too. But here's the idea that if f and g are defined on the same interval, then the antiderivative of f of x plus g of x can be broken apart into the sum of those two antiderivatives separately. So the antiderivative of f of x plus the antiderivative of g of x. And then kind of squashing these theorems all together into one, and how we will ultimately use this in practice is the 4.1.7 theorem. And these are important enough to have their own names. They're just 4.1.7, 4.1.6, that we can combine this for any number of functions. So if, for example, f sub 1, f sub 2, all the way to some arbitrary number of functions, f sub n, are defined on the same interval, and you've got some huge kind of nasty antiderivative that's polynomial in nature. So like c sub 1 times f sub 1 of x plus c sub 2 times f sub 2 of x, all the way to c sub n times f sub n of x. The question is, what the heck is c? Those are just constants. But this antiderivative can be broken apart according to these theorems into separate antiderivatives, all being multiplied by the given constant that's attached to it. So this can be broken into that first constant times the antiderivative of f sub 1 of x plus that second constant times the antiderivative of f sub 2, the second function, all the way down the line. So this is all this is saying is that we can break apart polynomials and anti-differentiate one at a time. That is a legal move to do. And this is, of course, where c sub 1, c sub 2, all the way to c sub n our constants. And the last piece of this puzzle that will let us really tackle any polynomial function is 4.1.8, which is going to give us the sort of blueprint for finding the antiderivative of a power expression. That if you've got some exponent that is a rational number, call it n, and a rational number, then the antiderivative of x sub n, let's pause and think here. The antiderivative of this needs to give us x sub n. And so we know that the antiderivative is going to be some power function. Let's think, what would we differentiate to give us x sub n? How does the power rule work in the other direction, coming from the differentiation side? Well, if we want to end up with x sub n, we would need one higher. Okay, if the derivative that is yielded is like x cubed, the antiderivative would need to be x to the fourth. Okay, because x to the fourth, when you differentiate, you drop down that 4 and you take 1 away from the exponent. But then that kind of makes an issue. Because the 4 drops down, you're also going to need to somehow cancel that so that we just get x to the n. And so what the antiderivative here is, and I think as we start to do these, you'll kind of be like, oh, okay, yeah, that sort of checks out, is that the antiderivative is x to the n plus 1. And so let's think about this. If we just left it as x to the n plus 1, that would get us the exponent we need when we differentiate this. And we would subtract 1 from this exponent, but it also drops down an n plus 1 as a coefficient. We don't want that. And so we need to divide this by n plus 1 to cancel that out when we do differentiate. And then not forgetting that we're always going to add a constant, plus c. And the one caveat here would be that n cannot equal -1. N cannot equal -1. Because if it's -1, then that becomes x to the 0, and that would get kind of weird. So we'll look at that case eventually. Okay, so now all that notation is out of the way. Let's just see, can we find some antiderivatives? So this will be illustration 3, not fancy enough to be a full-fledged example yet, still just a lowly illustration. I'll just run through a couple of these. So if we want the antiderivative of x squared, let's think about it. The antiderivative of x squared is going to be the function that when we differentiate it, gives us x squared. So this matches up pretty well with this theorem we just wrote down, but I don't want you to be just solely thinking through as the theorems. Just think logically. If we want to end up with x squared when we differentiate something, we should probably have an x cubed involved there. Okay, so x cubed, all right, the derivative of x cubed is 3x squared. That's pretty close to what we want, but not quite. That 3 is messing us up, so we need to divide that by 3. So now when we differentiate this, x cubed over 3, that 3 drops down, cancels with this 3, and we have x squared as we need. But we cannot forget, and this will be a constant pain in your guys' rears if you forget this, you got to add c. Okay, because this could be x cubed plus 10, and you'd still get x squared. Sorry, x cubed over 3 plus 10, or whatever you want to add to it will still get you back to that derivative. Okay, so maybe if you want, pause now and do this next one on your own. X cubed dx. What is the antiderivative there? Same thing, same idea. Increase that exponent, then account for that coefficient. Let's see. Okay. Now this works for not just whole number of exponents, but any rational exponent. So if we wanted to find the antiderivative of 1 over x squared, we can turn this into a power function. Right now it's rational, which we don't really know how to deal with right now. But if we treat this instead as the antiderivative of x to the negative second power, now we're in business. Okay, now we're just following the same process. We're going to, and I'm going to do this kind of slowly just so we are clear here. X to the negative 2, we need to add to that exponent. And then we're going to take care of the coefficient by doing negative 2 plus 1. And then all still plus c. So negative 2 plus 1 gives us x to the negative 1. Down here, we also get negative 1. And then just rearranging this so it's a little bit nicer. X to the negative 1 is, of course, 1 over x. We've got this negative out front. This is a negative 1 over x plus c. So that's how we could turn rational functions into polynomial functions, is making those exponents negative and then applying 4.1.8. And then finally, this will also work for radical expressions. So if we want to find the antiderivative of the cube root of x, and these are the ones that, so even as calculus students, you guys seem to not be big fans of fractions, especially when they're exponents, but you got to get over that. This turns into the antiderivative of x to the 1/3 power. And now, same thing, you can just apply this theorem. And yeah, it's going to require you to add fractions, which I know is a terrifying prospect, but I promise you can do it. This becomes x to the 1/3. We're adding 1 to that exponent. And then down here, we're taking 1/3 and adding 1. And not forgetting that constant as we go. 1/3 plus 1 should be like 4/3. 4/3. And then you can just leave this as, maybe clean it up and say, we'll call this 3/4 x to the 4/3 plus c. And I'd be fine with that. The main idea here is turning this radical expression into a rational exponent and then applying 4.1.8. Okay. All right. So now we're going to kind of start to run through the gamut of some more difficult ones. So we'll do some polynomials and see how that breaks down. And then we'll look at a couple rational ones that we'll fake into polynomials. And then depending on how long that takes, at the end we might touch the trig stuff, or this might turn into a 3-parter. Just kind of depends. I've currently got my brother and sister-in-law holding our child, and they're having to listen to me lecture on antidifferentiation. So the goal was to have baby fall asleep, but I think brother and sister-in-law are also being put to sleep. So we're gonna try to be cognizant of that. Yeah, illustration 4. Let's do this. Looking at polynomials. Woo! Scott, do you remember what polynomials are?
Many numbers.
That's not a bad definition, actually. Many numbers. That was my brother. It's been a long time since he's taken a math class, I would guess. Okay, so we're going to look at the antiderivative or the integral. We try to be upfront about the fact that very soon we're going to ditch antiderivative and just call them integrals. So the integral or antiderivative of 3x plus 5. What function will give us 3x plus 5 as its derivative? Well, we can apply some of these theorems. We're going to be very deliberate here and break these down, much like we did when we first saw the limit theorems and the differentiation theorems, just to show what's happening on each step. Eventually, we'll just look at this and say, go to the final answer. But I do want us to sort of deliberately break these into smaller parts as we go, so that this sum then can become the sum of two antiderivatives, namely 3x and 5. Pulling out our constants here, we have 3 times the antiderivative of x. And we have 5 times the antiderivative of just 1 here. Okay? So now we can actually take these antiderivatives. Again, eventually, we'll just kind of go to the good part, just showing that this is the nuts and bolts of how we're getting there. And so this is going to be 3 times, if we want the derivative to be x, what we'll be looking for is x squared over 2. And then the antiderivative of 1 is just x. All of this plus c. Oh, yeah, I guess I'll be, yeah, we'll be stingy here. So I sort of messed this up. That's okay. I haven't slept in a while. Hopefully some of you are yelling at your YouTube, but probably not, that there needs to be constants here. Okay, we just took an antiderivative. The antiderivative of x is not x squared over 2. It's x squared over 2 plus whatever constant we might choose to add to it. Okay, so plus we'll call it c1. And this will actually be a somewhat important point, which is why I'm actually going to show this. When we differentiate 1, we know that the antiderivative of 1 is x. The derivative of x is 1, it works. But this will create another constant. Okay, because really x plus anything has a derivative of 1, not just x. So that's a little bit troublesome, but in a second we'll see that we're never ever going to do this again. We're never going to do 2 constants, because this becomes 3/2 x squared plus 5x plus, we'll distribute this 3 and call that 3 times the first constant. We'll distribute 5 and call this 5 times the second constant. But let's consider this. These are arbitrary constants that are just being multiplied and added together. Okay, this whole thing is arbitrary. There is no purpose to listing these separately. Okay, this is unnecessary. And that word has too many, I don't know, I think that's too many C's. I don't, yeah, okay, not needed. And so we can, in fact, forego these separate constants and say that the antiderivative is just 3/2 x squared plus 5x plus c, just a single solitary c. I mean, if you want to think of it, this c is just kind of morphed from these two, but it's still just a constant, whether it's 3 times 5 or whatever, just a constant. Okay, and then it's always a good practice, especially as we're just starting this process, to check your answers. How? Whatever you said the answer was, differentiate it and verify that you get back to where you started. So the checking process is to differentiate your answer. You should never walk away from one of these problems unsure if you have the right answer, because you'll be able to check it. So in other words, we're going to take the derivative with respect to x of 3/2 x squared plus 5x plus c. The derivative of 3/2 x squared, that 2 drops down, leaves you with 3x. The derivative of 5x is 5, and the derivative of c, or remember, c is just some constant, 7 or 17,000, doesn't matter, is just 0. 3x plus 5, oh phew, we got what we started with. So we feel pretty good that this is our antiderivative. Okay, so now we're going to do an example where we're not going to mess around and separate this. We're just going to go piece by piece and find the antiderivative. So kind of a jumping up in difficulty a little bit to a bigger polynomial. Example 1. Finally reached the examples on a lot of illustrations, but now we're in the big leagues. Okay, so probably should have skipped a line there. Oh well. The antiderivative of 5x to the 4th minus 8x cubed plus 9x squared minus 2x plus 7. We're not going to do what we did up here and break this apart. We're just going to go piece by piece and do it. So this turns into, well, we know that this is going to be x to the 5th over 5. But can't forget the constant out front. Okay. Minus 8 times x to the 4th over 4 plus 9 times x cubed over 3 minus 2 times x squared over 2 plus 7x. Okay. If you're not seeing where I'm getting these expressions, press pause, work through it piece by piece, but eventually we need to get to the point, not eventually, but pretty quickly, where we can just see x to the 4th, okay, antiderivative is x to the 5th over 5, and so on down the line. So these are the kind of very most basic, simple antiderivatives or integrals we're going to compute. And now we go through and clean this up a little bit, simplifying where possible. The 5's go away, we get x to the 5th. That turns into a negative 2. That turns into a 3, negative 1, and 7x. Oh, and I almost made the mistake. We can't forget plus c. Can't forget plus c. We'll do our check. The derivative of x to the 5th minus 2x to the 4th plus 3x cubed minus x squared plus 7x plus some constant. Derivative of that is 5x to the 4th minus 8x cubed plus 9x squared minus 2x plus 7 plus 0. Is that where we started? Well, happy day. Okay, so you have that reassurance each time you walk away from one of these problems that you have the correct antiderivative. If you don't get what you started with, you made a mistake somewhere, go back and find it. Okay, so polynomials, just like differentiating, are kind of like the baseline, pretty easy case. These next two examples, then I think we will call it a day there and just resign ourselves to a 3-parter. That's the way to start the new year. We got 2 more examples, and then we'll call this a day. And in these next 2, we'll move away from polynomials on the surface, but not knowing how to do anything but polynomials, we'll have to find a way to turn these functions into things that look like polynomials so that we can do what we're doing here. So starting out with some radical expressions. Radical, example 2. The integral of the square root of x times x plus 1 over x dx. That ain't a polynomial, okay? Because the part my very erudite brother left out of his definition was, yeah, a lot of numbers, but you can't have exponents that are not whole numbers. And I see there's a 1/2 in here, there's a -1. This is not a polynomial, okay? But we can kind of turn it into one. So let's see how we can do that. This is going to be the antiderivative, not of the square root, but now of x to the 1/2 times x plus not 1 over x, but x to the -1. Okay, but there's still a product in here, and that should kind of worry us because we haven't really talked about like product rule or anything. So let's distribute this and see what happens. What happens is x to the 1/2 times x gives you x to the 3/2, and x to the 1/2 times x to the -1 gives you x to the -1/2. Oh. And so now this is still technically not a polynomial, because again, to be a strict polynomial, you have to have whole number integer or whole number exponents, which we don't have. But we do have the ability to now use our rules of antidifferentiation to find these two antiderivatives with the power rule. And so we'll do that. X to the 3/2, the antiderivative there is x to the 5/2, adding 1 to that, divided by 5/2. X to the -1/2 becomes x to the 1/2 over 1/2, all plus c. And how much neater do we want to make this? Sure. So we'll call this 2/5 x to the 5/2 plus 2x to the 1/2 plus c. Do a quick check. The derivative with respect to x of 2/5 x to the 5/2 plus 2x to the 1/2 plus c. Derivative of 2/5 x to the 5/2, that 5/2 drops down. We'll cancel with our 2/5, which is nice. Subtracting 1 from 5/2 gives us 3/2. The derivative of 2x to the 1/2 gives us x to the -1/2. And the derivative of c is 0. And so this matches up with this. Now, yes, I know that's not technically where we started, but as long as you are confident that you didn't mess up distributing, this is a safe place to end, or a decent enough check. Okay, last one, and then we will call this a day. That was with a radical expression. Now we'll look at one that starts out as clearly rational, but then same process, we're going to kind of finagle it into a more polynomial-esque situation. So this will be example 3. The integral or antiderivative of 5t squared plus 7 over t to the 4/3, oh happy day. Oh, that's a 4/3 dt. Okay, notice that this differential part here does change depending on the variable that we're looking at. So we had dx up here, now it's dt. Again, we don't really have a quotient rule here, so we need to figure out a way to turn this into something that looks like more of a polynomial. And so we'll just straight up divide, turn this quotient into its parts. So 5t squared divided by t to the 4/3. When we divide exponential expressions, we subtract those exponents. And so this becomes 5t to the 2/3. 2 minus 4/3 is 2/3 dt plus the antiderivative of 7. Here there's no t here, so this just becomes -4/3. And now we can apply those power theorems to find these antiderivatives. Not the neatest situation, but we can make it work. This turns into 5 times t to the 5/3 divided by 5/3 plus 7. We'll add 1 to -4/3, which will give us -1/3 over -1/3, all plus c. And then cleaning this up a little bit, this turns into 5 t to the 5/3. Yuck. What are we going to call this? Let's call this minus 21 t to the -1/3 plus c. And then we need to check this right quick. We'll take the derivative with respect to t of 5t to the 5/3 minus 21 t to the -1/3 plus c. My computer still has juice. Good. Okay, so dropping down this 5/3, we end up with 5/3. Oh, I screwed this up. This should not be a 5, this should be a 3. This 5/3 flips over into 3/5. The 5's cancel and give you 3. This should be a 3. So what we end up with is drop down this exponent. We get 5/3 times 3t, subtracting 1 from this, gives us 2/3. Pulling this down, we get positive 7 t to the -4/3. And then simplifying this, we end up with the 3's canceling. You get 5 t to the 2/3 plus 7 t to the -4/3, which is kind of the second step from the beginning, but matches up well enough that we're pretty confident that we have found the correct antiderivative. Okay, so where that leaves us, our final section of this is we're going to tackle some trig problems, so seeing what are the antiderivatives of our trig functions, and I think that'll flow pretty smoothly. And then we will do a couple of specific examples where instead of ending up with antiderivatives with this general c in it, we'll be given some initial conditions that will allow us to find the specific antiderivative in question. So that's what's in store for 4.1 part 3. I think that's our first 3-parter of the year. So sorry, Winnie. All right. I will catch you guys later. Stop recording.